So here we are again. I'm actually now officially on my vacation, but I'm leaving on Monday and we'll come back on Thursday. There will be probably no streams about this, although I will probably be still working on parts of this. So, where did we last end it? I won't do full recap, but technically we had full one-way instruction encoding, so we were able to do these with the register on the left and the memory expression on the right. We were just about to add sub and add instructions, so let me jump right back to it. I've made some changes yesterday. I've made this x64 generator thing, and this one generates those files. So before I was using just the static file that listed all the test cases that I manually put together, but now I said fuck it and we'll just do something different. I want the test to be covered as much as possible. I want the test to cover every possible case, and then probably limit those that are a little bit either not supported by ML64 or have a special meaning, and I will test those separately. Also, this doesn't generate any error cases. Oh well, we will see whether there are some additional error cases. ML64 will say. But there will be separate generator that will generate the different set with all the error cases, and I will have to check whether my library is checking for those. So what it does is quite simple. It goes through every possible permutation of the instruction encoding, especially with the mod RM, SIB, and the order of arguments or operands. So there is we have these two sizes because we don't support yet S16, and S8 is quite weird because I'm not sure whether I will be using it, although it might make sense, for example, in case when we have MOV AL, CL, but in the C we would write that a little bit differently. We would do x64 MOV, x64 register argument, x64 RAX, and this will be the same thing on the right but with RCX. And this naturally will produce the MOV RCX, RAX to RCX, which is of course a larger thing. I'm not sure whether it even matters, because this one will do, if you are only dealing with 8 bytes, and if you only store like 8 bytes in a register, then this will make more sense because it will also limit it, it will also cap it on 8 bits. This would not cap it. If you have some larger value than 8 bits, larger value than 255, this one will just copy it there and will just not care. This one will basically end it for you. This is so this MOV AL works the same way as you would do RAX. Not sure if AND is even an instruction, but you get the idea. It's basically RAX equals RCX and this. So MOV AL will do both of those operations, assignment and ending for you naturally. So that's why I might use the sizes for S8, and the size goes here, of course. And yeah, size goes as a first argument. So here in this case, I would do this to force 64-bit transfer. So for example, if we know that we are storing 64-bit value in these registers, we cannot use S32. And there is no other way for us to know what value is there other than the user telling us that, hey, it's this one. What I might do eventually is also x64 default, and this will default to 32-bit possible. If it can detect that you are pasting, that you are working with something larger, for example, you are assigning constant value or immediate value to EAX, and this would be something way larger. So it will be, for example, yeah, this is not allowed, but let's do something like, yeah, this will definitely be larger than 32 bits, and that means that that the library will automatically always detect when it's on default mode. Then when you are on 32-bit mode, it will either warn you that it will be capping that value. It will be basically removing extraneous bits. So we will, in this case, you would actually end up with 4 zeros. And we'll do it for you, probably warn you. I don't know what design to use, because there is some logic that or some smartness that the assembler library has to provide, but also it doesn't have to guess. Don't want it to guess everything everywhere. So it's kind of like a sweet spot of just giving you smallest possible instruction, and as long as it knows that it's safe to do. Otherwise, it would either warn error or will produce larger instruction in case it's not completely sure what to do. Yeah, so the sizes are there. So we have these sizes, the default. I can actually write it down to my library that we will be using the default probably eventually. I don't know how it will work. Sizes are still a little bit foggy for me, how they should work. This is kind of a type, right? So this dictates what type of operands we are using. Although sometimes if you have the constant, it can infer that type and can do some better things for you without you specifying. Okay, so then we have scales. This is for multiplying the register value by 1, 2, 4, or 8. 1 means basically that we have no scale. Then we have these 3 displacements possible, which is 0, 8-bit, and 32-bit. And maybe eventually there are some instructions that can take 64-bit, but I think those I will test separately, not with this generator. Finally, we have some just the locals that define the registers, and here I construct like 3 arrays with those registers. So for registers, it's on the left or right, and it's just a single register. Then we test only for these 2 cases. I'm not using array-x because array-x is 0, and the library might do something weird and just ignore that value, and in that case we wouldn't know whether it generated correctly. So RCX is 1, and in this case we will be super sure that it's working. R9 is the extended register, so in case we need to know whether it correctly produces the 64-bit prefix. Bumbet, hello there. How are you today, my good sir? Even if you are a girl, you are still a sir on this channel. Then we have bases. These are basically the first, like, a base address value, or if we have this, then this is base index times scale plus displacement. So this one is this. So all the options possible for base, where R0 means what is instruction encoding. Okay, so it's similar to what you do with when you are making a language, and basically it's the same thing as assembler is doing. So it's kind of a assembler library. It's not assembler program, it's an assembler library that you can use in real time, in runtime, to generate code for your CPU. So you can generate in memory code for your CPU, for the x64 CPU, which is specific CPU, and then run the code. So you can at runtime generate instructions and then jump to that location and run it as it was a function. So this will give you several options. Most of the cases when it's used is when you are writing a language and you want the language to produce actual code that you can run on CPU. So we compile to actually CPU. This is what C compilers or C++ compilers are doing. Second option is really use it for some runtime things, where you can generate additional codes to the memory and run it, because when you are running it from CPU, it's or directly on CPU, it will run much faster than, for example, using a scripting language, which will run really slowly. And you can use it for some special things like special calculations or whatever. That case is not my target. My target is basically being able to generate this in runtime, but produced, but my compiler for my experimental language will use it. That language itself is embeddable, but I will talk about the language some other time, because we can go rabbit holes for all day long in there. God, need to do something about these spammers. So yeah, this is for all the variants for base argument. This is variance R0 means it's none, so base is basically omitted. There are also some cases. Then for index, again, list of possible variants. I have RCX in the base. Get back to the base a little bit. It's a RCX, which is kind of a normal 32-bit variant, but then we have these two special ones. These have some exceptions. These are exceptions in the manual, so I need to know whether these are generating correctly. Then R9 is basically first simple. These RCX and R9 are just testing basic cases. R9 would require the 64-bit prefix before the instruction. R12 and R13 are again behaving on 32-bit level the same way as RSP and RBP. So I want to know whether they generated correctly. Then for indices is the same kind of deal. RSP cannot be even used for index, so I'm not including it here. This would mean that I will have to test for this as if it was an error case later, which is this test. R9 again, the same deal. R12 is same deal as RBP. I mean the same deal as RSP, except I'm not sure whether this will be possible to generate, because you cannot index by RSP. But I think you should be able to index by R12. Why this is the case? It's again because these 8 registers are the base registers for on 32-bit, and then 64-bit would add these extra registers on top. So registers are encoded with 3 bits, and 3 bits maximum value they can encode is 8. As far as I'm not, it's 1 plus 2 plus 4, which means 7, including 0 value. Then you will have 8 registers. So if you want to use these extra registers, you have to add one bit, and this is added through additional prefix. You stuff back bit before the opcode, and that means that on all the encoding, registers like RSP and RBP are encoded the same, or registers like R12 or R13 are encoded the same way as 2. So they have some common behavior with, or share the behavior with these two, and I want to see how that will work. So we will see. So these are the indices, and then we have we already went through the scales, and displacements are here. Really testing just 0, 8-bit, and more than 8-bit. This should eventually encode to S. So this is first generator. This generates register to memory variant. it actually registers the opposite one, memory to register as well. So what it does, it iterates over all possible sizes, all possible register spaces, indices, scales, displacements, and then has some special casing for some special situations where, for example, everything is 0 here, including the displacement. So the whole right side would 0, so it doesn't make sense. So you cannot assign nothing to register and just go through. And this is a case when that forces us to not encode any other scale. If the index is 0, we would always go with x1 only, and everything else will be ignored from POSIX. This produces two things. One is assembly instruction for that. Let me open that. So it produces this thing. These instructions, you can see that it generates this line, and then later it generates the other way line. Basically the same things, except it's operands. Left is on the right and right is on the left. The second line produces the C code, which in this case is this line, which is my library thing that is supposed to generate the bytes. And again produces registers in a normal order and registers in a reverse order. So you can see that RCX is on here, on right here, and memory right here. And it stuffs it into a giant table and returns. Then my build tests, instead of reading, before I was reading this from a file, now I'm not. I'm just asking the function to generate that. So this will be a giant table, .a for assembly instructions and .c for C instructions or C side instructions or my own library instructions. It will produce the assembly code, assembly file, this one. It will compile it. Then decompile it. So we get this insane file, which will tell us that, hey, your instruction is this, and the bytes used to encode the instructions were this. So this is like a thing that we expect our thing to produce as well. And we will parse out these bytes in order to generate. Well, it's not written here yet. Yeah, it is. It's here. Yeah, so it will generate these strings from these values, these bytes. It will generate these strings. So our test function, which is x64 test equals, will check whether our thing basically produce the same bytes as ML64 assembler. That's kind of the idea of the whole thing. This will basically cover all the possible cases of all the instructions that we care about. Currently, we only deal with two instructions, which is mov and sub. And when I run it, it actually failed right on the second line, which means that we are missing the case for arguments to be reversed. So when memory expression is on the left and register is right, this will need to encode with a different opcode. We see that this is 8B and this is 89. So 89 says that, hey, the arguments are reversed to 8B. So we need to add this special case. It makes sense. Okay, I will have to grab something for drink because my throat is parched. Let me check how the stream is going. Actually, I didn't even check it when doing some. Okay, it seems to be doing some things. Okay, so let me grab something real quick. I will be back in a few minutes because I want to make some coffee as well. Okay, and I'm back. Good. So, we need to generate this opposite version from our code, and that's let me turn this off. And yeah, so how do we do it? This is the function x64 mov, and it calls emit binary, and emit binary is here, and it checks what the order of the arguments is, which is supposed to be here though. So it takes each operand, it has a kind, and that kind is either reg or other edge, immediate value, or a memory. These are three possible values that the kind can have. And then it encodes, so we can take a look at x64 operand structure. This is the kinds possible, and here is the basically tagged union that I'm using here. So in case it's a register, it will have value here. If in case it's a memory, it will have value here, and in case it's an immediate value, it will have value. Idea. Yeah. Okay. There are a lot of things that I don't know about instruction encoding yet, so this is kind of a learning process for those that know. Anyway. So if the register is in the on the left, which means it will be in E, and the memory is in S, then we call this function that will encode whatever is in those operands. So here we need a second case, which will be basically opposite one. I can do it directly here, because the only thing that really needs to happen, as far as I know, I can do it here, but then I will move the code somewhere else. So if it's the other way, then our emit binary is expecting, because this one is expecting register on the left and memory on the right. If it's the other way around, it won't work. And it's not even checking for that case, so it should probably check for that case eventually. So what we will do is that we will swap the destination and source operands, and we will force this to be called anyway. So it's really simple. Operand P is S, S is D, and D is S. This will basically swap our operands, and that's the whole idea. Then we basically fall through, and it will call our thing with the registers the other way around. The problem is that we are we need to encode different opcode, because the opcode is dictating the order in this case. So we are passing the structure of binary, which has all the possible variants of the opcodes for various cases. I'm not covering all of those yet. I just wrote them here to know, but I'm only using like this one, this one, and these other ones are not yet used at all. I will eventually plug them in, because they give us some possibilities of making instructions smaller. We have a variant smaller than we should definitely, unless it will have some side effects that we don't want. I think there are some side effects of some instructions, special handling needed of those instructions. Some of them cannot encode all the registers. Anyway, mov instruction is defined here, and it will be basically passed this thing from here. Emit binary will call it with this constant structure. So this function can actually choose which one of these it will use. But at this point, it only works in one way, and it will always pick up only that one thing. So obviously this detection shouldn't happen here, otherwise we would have to change or decide about the opcode here, which maybe is a good thing to do, but I don't think it is right now. So that's why I'm not going to waste any time, and I will just implement it how I think right now it should work, because you can then, oh, I closed it, that fingered it. Okay, so in this case We are inside of that instruction, inside of that emit binary regmem, which expects the destination operand to be register and and source to be memory. So we can detect those operands here. So we can do switch, and I have a macro that will extract the pair from there, and if it is x64 register and x64 memory, then we are okay. All good. I usually write these cases here, and I expect the compiler to compile them out. And if it's the other way around, it's 64 mem and register. Did I bro? No. Sometimes I use this like O for operand type, and sometimes I just put in a 0. Just muscle memory, which is quite weird. But yeah, I will probably have to change it. So in case it's the other way around, we will swap the operands here, and now we have an opportunity to choose the opcode. So I will check out where the opcode is actually selected or used, and we see that it's right here. We just use one opcode, which is RM for MOV, which is rec RM is this one, 8B. 8B, and it will work for this case where registers on the right and memory on the register on the left and memory on the right. But for the other case, we need to choose the 89 opcode for the other way around. And now we see that we are choosing this always, whatever the order is. So we will need to choose this one in case it's the other way around. So what I will do is really simple. I will just put the opcode here and here at the start. I will define the opcode. I zero it because eventually I might want to check for it. I don't want garbage in this case. Generally, I don't care because I know I will assign it, but this is special. So in the case that we pass something weird in there, we even will just fail here. I don't think I have my fail from here yet. Yeah, I will do error. Because this needs to fail. This is internal function. You can, I still keep it public, because you might want to use them for something else, for something that the library wouldn't be doing. You might want to use them for some special encoding and then processing on top of that. So I'm trying to keep everything public. But it's supposed to be used by somebody who knows what he's doing. So that's why I keep the underscore after the like my. All right. So in this case, the opcode will be op.reg register on the left and memory on the right. But in this case, it will be the other way around. And here we will check whether the opcode is set. And if it's set, we need to check whether it's 0, because there might be functions that, instructions, the structures, where is it? I need to define all these values manually, so I might forget about them, or they might not even have that variant. That case, I will probably have to do something else, probably error. Maybe there will be some option based on operands that, hey, we have option for this because it has this special opcode, and we can encode this, but we cannot encode any other case. So in case the opcode is not set, for now, we will just error this way. This macro will basically abort at the moment. That's what it's supposed to be, because it's invalid use of the APIs. However, there's another options of pushing out an error, and that's I can return I can return error in this field, and this will fail gracefully, so the user of the API will know that, hey, it failed, and we cannot encode this and can do something about that in runtime. So we don't want this to be failing all the time, or just crashing the application down because somebody did something. I know you might use this for actual assembler, and that will mean that if user makes an error, you want to inform him not to crash the whole application. So in case opcode will be 0, it means that it's a code error, and we cannot do anything about it, and the user cannot do anything about it because that definition is missing. So in that case, we'll just opcode is not defined. Okay, we might be more specific here, like do the error right here. And have better message in here, but since the code is quite simple and you can already check whether what the kinds are, and now we fail here and we can return. I need to return because sometimes the compiler thinks that the code will continue, and this will tell it that, hey, we are not continuing after that. Consider that as the case. Abort. I'm now using abort function by default. This I think has the flag on it that no return. Yeah, thank you. MSXML, yeah, that's exactly where it is. It's an argument in MSXML header. Oh my fucking god, this just sucks. Okay, so yeah, abort should have no return flag on it, so compiler will know that once we call it, nothing else happens in this function, and now we can just crash at that point. We don't have to consider the code after that. But yeah, sometimes you want to use something else. You might use long jumps or something like that. So in that case, or your own handling of some sorts. So in that case, we need to specify that, hey, this will just exit and don't care anymore. Okay, so opcode is not defined, and now we can basically test it through. I will first compile because I'm sure I made mistakes. Of course I did. This is the, yeah, of course I did. In this case, we are ignoring the message. Should probably print it out, but I can use something else here. But I think in the tests I already redefined the macro. Yeah, X error message. Can pass it to this one, and co fail is my function. Co, come on, co fail. So who will be faster, me or that fucking thing? Yeah, so it's, yeah, no references. I just fucking found it, man. It's just right here. Come on. So it's message, and then we can have arguments, but we will at this point x64 error. Play. That's it. So it will write the error out and finish. We'll call abort. It's on it. Abort. It's fine. So. Okay, so this will do the thing. In case ambiguous error happens in the runtime. Yeah, and this is something. So we return 0, and here we set error was. Not sure even why was this. So like completely new errors in here that just, oh my god, what the fuck happened? Microsoft compilers is not really good at these things. Really doesn't help you too much with, but I'm just stoked that actually it was just compiling, it just worked. Like seconds ago, before I started the stream. Yeah, so in case IT will be 0, then we return x64 and its error, which will return instruction, but with the error field set. The error here, and error here. And it's already set it to something. Unknown error. Wait. Okay, awesome. Yeah, this will be any error, but just a string. I will need to go through all the errors I return, because that way I can I need to have them like concept, and I will go through them and make sure the errors make sense. So, but it's not the important thing now. So it compiles, and I have written the test with operands reversed, and we expect 89 to be instruction code and then encoding. So, okay, awesome. So this will jump to unexpected because we only expect mem or reg. So, I mean reg on left, mem on right. So we will add it here. In this case, it will allow that case to be passed through this thing because it's the same, and functioning side is handling it now. Let's go again. Okay, we are jumping here, opcode is 0, now we detect that it's the other way around, so we swap the registers, swap the operands. So S is now memory and destination. What have I done? Oh my god, yeah, the swap code is perfect, amazing. Okay, go here. Them. Before it was memory on the D, now it should be register on D, and S should have memory. Yeah, right? It works. Break. Opcode is not 0. Let's check what the opcode is. 137. I would like to know how to switch this fucking thing to use hexadecimals. Doesn't, so 137 is 89, which is what we expect. The first thing. Yeah, so we go through the thing. I will just quickly check whether it doesn't do something insane. It sounds like it doesn't. Opcode is encoded. Placement. Yeah, break. No error. Action is set, and we pass. Okay, passed. Great. So we can remove this case. The problem with these tests is that it's quite a lot of tests. Even for I have now 2 instructions there, which is sub and mob, and it already is on 21,000 lines. Okay, I do have some empty spaces, empty lines, and some comments in here, but still, it's just quite a lot. So it takes a lot to compile. So that's why I will probably keep it. It generates quite fast, to be honest. But compiling takes much longer than I'm okay with. And I also had to raise the stack size for it for some reason. Not sure why, to be honest, but I guess each of these produces some value on stack. And there's also a lot of strings. Might be relevant to that, but it may just be because there is a lot of code. Maybe as simple as that. Okay. So it didn't run. I don't know why, so let's run it again. Always compile. I don't have any checks for changes in the source code. Always compiles. I never had actually anything compiled this long. But I will run this only occasionally. Now I need to make sure that all the cases are coding correctly. Hope that now it will work. Oh, thing. Oh, there is. Good. Okay, so this one, and it's quite deep down. It's a case when the displacement is 0, and for some reason, it's just simple registers, 32-bit ones. This is times 8. And for some reason, the ML64 decided that we need zeros encoded here. And I'm not sure whether it's because this is plus 0h, and if I would... Okay, I will try to compile... Oh my god, sorry, that's my dog. He's a little bit weird today. Okay, I will need to take a little bit time for now. Going for smoke and a little bit of coffee, and I'm right back. Okay, so I will have to try whether this needs to be omitted completely, because ML64 is quite close to whatever you write there. So if you explicitly write 0h, it doesn't try to be smart, really. But I see here that we have actually encoded that thing in there for some reason, which is weird. I don't think it should be really encoded. So let me try GCC. For GCC I have not now, but here. Yeah, I need to enable my screen as well. So at least I get to. Yeah, I closed it conveniently. Okay, enabling screen, and x64 disassembler, and it's this. So I will put this here, without this. Switch it for mode. Yeah, and it's forcing that displacement in. And I'm not sure why is this happening. Expecting that to happen. So need to check it, because I think there is it's actually in some mode that makes it do that. Instruction. Okay, so we do have sib byte in there. I can actually go through the code. Now so let me copy it out, just that one case, and put a break. That's the first thing. Then second thing is why it doesn't match actually. Do correct thing in there. So we choose normal to register to memory with. So this is index only. We can go through code, calculate displacement. Index is something else. We switch the mode RM to be. So far the mode, which actually dictates whether we do have displacement or not, is 0, which means that we don't have any, but I think, yeah, so we have to flag that we are not using any base by setting the base to RBP. RBP indexing is different. We're setting the mode to 0, forcing it to 0, but the displacement has to be. Okay, yeah, so that's it. By the manual, and obviously ML64 does the same thing, and that's all right. And then we are wrong about the SIP for some reason. Quite interesting, because GCC says that it should be 8D as well. So this, and we are producing CD. So we will check what the CD is. CD binary value is this one. So we split it like this, and this means that we have 8 times scale. 001 is RCX. So this is SIB, so this RCS is used as index, that's correct. And this 101. And it shouldn't be 101, because base is, yeah, this is RBP, I guess. So 101 is 5. 5th register. Let me check, I don't have these register numbers. I will just write them here. This will be the bit representations. Yeah, 101 is RBP. Now we copy this. Oh. This is one dot. Notation. Okay. So 101 is RBP for our case, but they encoded with 8D. So this is CD, and it would be 8D. 8D, 1, so I already see that there's an RBP. Oh, I see. 8D, and this is 10. Did I mess up? Is this times 4? It's not times 8. Yeah. Yeah, so it only differs, the registers are the same, but this says correctly, to be honest. It says 4 times, but our code generates something else. So it's actually the scale that is wrong here. And I will need to check why that is. We want it to be times 8. This is what we want, obviously. But it seems that the actual code for... Yeah, the code for multiplier is different. It still says times 4 while we want times 8. So this is not even a problem in our code, it's actually a problem in... but this would be... yeah. We will have to check this line, which one will... on line 68. We'll put bookmark it. Line 68. Okay, so this is problem in the generator. Okay. Sizes. This is scales. The scales is these things. Yeah. This might be the problem because it maps to value 4 while it should map to value 8. Oh, really? Yeah, and this will work. Okay. So I need to regenerate thing, but we don't have to compile it completely. Just regenerate. Yeah, times 8, and now it says CD and not 8D. This. Yeah, so that will work. Let me fix everything in here, so we don't need this one and these two, and we wait. So after I've done these, hopefully we will see how many errors we have. Hopefully there won't be that much of them. Problem is that we have to wait for all the time. Okay, it's running. Oh no. So this produced we produced smaller code than they did. So okay, let's check the GCC one again. First, after expression, young after expression. Is this supposed to be? All right. Yeah, it says that I put it. Yeah, it was. Yeah, okay, it was different notation. Yeah, so it says that it should be the longer one as well. So we now need to check what's wrong with that. First, let me check whether it's generated correctly. So C register on the left, then RBP then RCX as index times 1 and 0 for the display. Okay, okay, so let's check this one and go through it, what's wrong. And we expect the value to be this. Yeah, so let's go. So we are, let me see. Yeah, we obviously are missing the displacement bit in here, and our SIB the same as the yeah, it will be probably problem in the mod RM. So this is OC, and OC is just this one. Let's fill it in with yeah, and this is mod RM in this case, and 00 says that not any displacement, which is why we then don't encode it, but it seems like this case incorrectly. So 8E 4C is this one, and 4C is this one. Yeah, it's 01 case, which says that there will be 1 byte of displacement after the, otherwise the registers are. So the problem is that we have to produce displacement, but we are not detecting that case. Okay, so let's go and step through the whole thing. Oh my god, come on. Just compile what I mean, not what I wrote. Dead hard. Okay. Now we detect that the displacement is 0, and we think that there will be no displacement. Other options are these two by the size of displacement, and then we go like this case. M base is actually RBB. Oh, I see. I think there will have to be kind of this logic. That's interesting. Okay. So yeah, this logic needs to be there. So if the base is RBP, then we need to. Yeah, it already does it here, but. I will probably have to reorganize the code when it gets complete functionally, because it seems that we have a lot of overlap in these two cases. I have a case when we want index, so we this is special case, we don't care about that, but this is the branch where index is 0, and obviously you can see it here that this is the same, then this is now the same, and probably we will have problem with this as well when the base is RSP. Otherwise we check these things, and yeah. So these two parts, in case index is RSP or index is 0, need to have like a common ground. So probably we can do the decision somewhere else. Oh no, it's not that. When index is not RSP and it's not 0, then we go to a part that is quite similar to index being 0 case. Okay, so let's run it. Base is 0. Yeah, that's interesting. Up. We are encoding this one, and C base is 0, which shouldn't be. So if the I will need to check this again, because it seems like we are not setting C base to anything. Well, in this case, it should be actually set to, yeah. So this should probably be here, even if we are overwriting it here. And that should do the trick. So once I have the logic, oh my god, I skipped over it because but it worked. Okay, it works. It works. So let's get back to this. Run it. So I will need to optimize the code eventually, and I'm thinking whether it's possible to encode it in a way and make it way smaller, because now it's quite a lot of code in there. It's quite complex, and once works, nobody should ever touch it, to be honest. Once the tests are passed, I expect now there will be special case when RSP is used as index probably, although I'm not sure we even generate that. Yeah, so we passed. We passed. Works. So I can do one more thing here in tests count and just increase it every time, because I want to know how many tests we actually have. Will of course take a little bit to compile again, but I need to know how many there is. Because I like it to be a big number, and then I like to brag about it. Why I like big number. Zero. That's oh my god. Did I mess up? Did I messed up? Go through these now. One. Tests count. Oh, of course, because yeah, of course it's yeah. It would have been even better if it actually picked up something from the stack, like some garbage, and said like, "Hey, you have 2 million of tests," and I would go brag about it and find out that I didn't put a fucking argument to printf, and it was just stack garbage. Okay, so once we have these, then we know that both and sub work correctly for most of the happy path tests, or for all of them, technically. Yeah, 7,000 tests. That's quite a lot for just 2 instructions. So yeah, once we have these, so we have covered these 2, and now we have to cover pop and push, because this will give us possibility of generating tests for unary instructions that take just 1 argument. So let's do that. What I will do is that I will probably turn this off, because every time we then run the build to generate those tests, we will have to wait for compiler as well, which we want. Okay, so local function unary, and we have operation, our opcode, and in this case we can just do this. Yeah. So we have only 1 operand. That means that we just, but we also need to generate all the memory case. So I will do it like this, because I know that pop doesn't have memory option. It only has the argument cannot be memory as I don't know. Maybe it can. I definitely don't encode it. That's given. Doesn't have the immediate value. It doesn't have the value. Yeah, we will have to do. Oh, right. also to do, there is another bunch of variants, and that's register to immediate, and there is also memory to immediate. So we will do the register. We can pop to memory, I believe, but we cannot pop to immediate. Yeah, so pop will be special. Push, you can do all of them. Push, register, memory location, or yeah, so those will have to. Okay, so if we are only having one thing in there, and this is not even taking the size now, which actually should. Should it? I think you can push and pop 16 32-bit values well, but I don't know how to encode them. I know how to encode I know how to encode the I don't know. We can check. Can we pop ECX in this mode? Oh, okay. So I guess these have to always be like AL. Yeah, so this has to be always 60. Case of pop, that means can push to that. Can we push AL? No. So or ECX. ECX. Yeah, cannot do that, right? Yeah, we can push and pop only register size. So pop and this thing doesn't take that. But there might be cases when unary have to take size. So we will deal with that case later. So we don't do sizes for now. Unary 64, because this will be always size 64. This one, and argument is register, so operand size is not there, and we only have this, and we have to generate pass the 64 size there, but so we can generate unary 64R for pop. Out. We can also do that for push, of course. R, and now we do 64M. This is only encoding memory. This one, and we need all these, so displacement, basis, and size, and also size. Yeah, so in that case it has to take size, because but for push the size will have to be on it's like it. Yeah, so this will go away. Memory and BISD. We force the size to be 64, and here it's M. This just thinks about it. BISD. Okay. These are those two. Now generator, and we need to define these two functions that generate the unary assembly. So it's register, operation, size, and we have a register, and this will return format this, and this is ASM register SR, and this will be the same deal, except we now accept BISD and put it here this way, and this will be SMM. Okay, so R, pop can do the memory one as well, push can do also memory one as well. I will have to do the error cases. God, there is so much stuff to do with these. So, pop. I have to note them somewhere. Eventually I will have them noted all over the place. But when I get these few instructions that I need to have in, I will probably go through that and try to fix them, go one by one in the manual as well. And we'll see. Okay, so this should generate the thing. So let's run the build. 197. Yeah, of course. Mixing languages. And I will have to do these two. Do 200. Yeah, too many ends. Too little ends. Failed. Oh, I hate these. I need to do better. This failed, so register it. Weird. And we go from this thing R, and that goes from thing. It should pass correct register there. But then we are not. Oh no. Let's see what flows there. The register is RCX, then we run it through. Oh, size. I missed size as well. That might be the reason we didn't pass the size. And it has to be this. Here I'm forcing it to be this, but I want the size to be x64 S64. Because I need to translate. This is based, like a first thing, all these things contain C expressions, or C symbols. But when I'm generating ASM, I need to convert them to ASM symbol. Size will be expressed in different ways than this that I use in C for my code. So yeah. Okay, so it generated all those things. Oh, it's not in the generated because I think I should. I'm generating these files and it keeps confusing me. So we have push, and it actually compiled, yeah. So you can actually push keyword. So all the versions for push and keyword. And oh my god, so much. There's pop to memory. Yeah. Okay. But so we don't have to wait for these because these already completed. I will do. I will comment them out in the tests. Don't have to wait so long. x64 tests. Okay. And I think it will fail on me not having implemented the memory argument. Yeah, immediate values are not supported with this operation. What the fuck? Oh, it went okay, well, but I commented incorrect line. Yeah, so I'm not better. So if whether I'm streaming in the evening, after work, or in the morning, I'm still same, about as much as samely retarded. It doesn't make a difference really. Yeah, I thought that I will be a bit smarter in the morning, but I'm not. Currently not when I'm streaming. So what we have a problem here is that we have error invalid register, which came from here. So if we check the pop code, which is for unary, we'll see that it only takes, doesn't have thing in it. So I will go through this one. But I only need this case. 4H. It's weird because I would expect it to jump on that to do thing. Oh, right. So I'm retarded. I'm testing there is register or not at the start, whether regardless of what the actual operand is. So this time it should hit that to do mark. Yeah, right. That's it. Now we need to encode the. Now we need to encode the memory thing. So that's the memory expression. Whoa! And I don't know how it will work because it consists of three things. It's this mod rm and then mod rm byte, and it's a zip byte if you want indices, and placement. And I know how it works for binary operation because mod rm would hold the destination. It has a space for a register that is on the one side, and then it has space for the expression that is on the other side. And I'm not sure, in case it's unary, what to do about this register. Like, yeah. And I think I will definitely need all this code for unary as well, so it's not binary specific. So I need to pull it out. That's something I know, and that means that I will just get it out. This is all the emits, write bytes. Yeah, and it will have to return something that we can code, so the thing will change a little bit. I will first write opcode at the start of this. Or we can actually just call the binary version of it. You cannot call the binary version because this one expects the binary operation, but pop and push are defined as unary. We'll have to find how to reuse this. I can doctor that, I can hack it in so that I can call binary reg memory from unary operation. Maybe try that. Yes. So here we will doctor the thing. So we want to call this thing. We want to give it ID, that's okay. The size, we'll give it size. Because I don't think we have it though. We can give it always, for now at least, x64 as 64 size. and then I need to construct this x64 up binary thing, and we'll need to encode rem, which is yeah, we won't do this. We won't do the memory register. We'll always call it as if it was register and memory, but we will set the register to be, I don't know, RAX, that is zeroed, and we will see what it does. So we will only use this one for the operation, and we know that we will use the RM operation in here. Everything else will be set to 0, so we will pass the binary. Then we have the x64 operand, so I can just generate one, which is x64 RAX. I think RAX is other register. Reg is ignored in this case, so we'll just pass RAX, which will encode as, and then we will pass our expression, our operand. This one should be the memory one. Do you have anything else? And the error, of course. We don't do error for these, so error. Like this, and return otherwise we break. So if it returns 0, it means that there was an error, some kind, that we will set and wrap it in the instruction structure. Pass RAX, which yeah, so we will see. We should hit this one now. Of course there will be compilation errors. Yes, of course there is. I had like time when I didn't hit any compilation errors with C. Days I seem to hit quite a lot of them. Okay, so we get here, that's correct. Go to this thing. We'll pull the opcode. What the fuck did I do? Yeah, so we need to check how this thing, its opcode is 0 because we didn't specify it, probably for pop. Yeah, so we need to find the opcode. Let's find the opcode. A black border. Yeah, I have a black border around because my main screen is not 16:9. I believe I might need to check those settings because it might be set up for 16:9 for some reason. Not sure how these work on Twitch though, so we will see. I will check it. So we need to find opcode for pop instruction that takes memory location. MPO, and that's it. So pop a value from stack, and we need this one 8F because this takes memory location. So let's do that. And we can also check real quick. Yeah, it should be 8F. So yeah, we did it right. Let's debug again. also I need to check whether there is some... No, it's just straightforward. Cannot encode 32-bit operands. Seems to be a lot of these small nodes that I will need to check. It's starting to be really tedious to actually do these things. To do. Okay. So we are here. Then the rec RM should be set correctly. Yeah, 143. When we go here, opcode will be set the same thing. Great. Register will be RAX, which means that it will eventually encode as zeros. There is no displacement. Probably there. Here. It seems to work correctly. Okay, so we produced oh, and it seems that in case of pop operation, we don't have to encode the rex prefix. This one. Because it's already given, like when you are popping, pushing, it seems like you always are dealing with 64-bit or whatever the default is. We're compiling for 32, but we only care about it. So in case, so yeah, this whole part needs to be optional. And now I need a way how to tell it that shouldn't, because it now is detecting that it should produce, because the size is x64. That's why it does this. So technically, if we, yeah, this is probably a good time for having these binary, and this is as default. Probably good time to do this thing. So we want the default, which means that we don't want any REX prefix, as long as the instruction is just natural. So if it's default, then we are not forcing S64. Okay, this should work for this case, as long as we ask for default size, because pop is just defined by. Okay. Fast. Okay. So it will work for now. We will see, maybe the code will have to change eventually. But let me run the full test. Remove the scale must be set to 1. Set to 2. Okay. Here, and memory scale is set to 2, and we have no placement. That's weird. That's incorrect data. Yeah. We are missing the condition in there, so we will do that. if that's the case, like wouldn't produce anything reasonable. Just right. Request. Code is not defined. And it's for also invalid case. So we need to copy the other thing too. So it's not only this condition. On top. So if all are zeros, then we cannot just do them. Slow reply. Yeah, I know, I just don't pay attention to it. That's all. Upcode, okay. What the fuck? Yeah, we don't have the push version, so we need to find the opcode for push. So we did the pop, but now we are in the push thing, and we need this RM thing. So again, manual. We do the push thing here. So for memory, it's this one. It doesn't have any nodes, so it's FF. In only have the displacement, all are technically zeros, but we are producing mod RM. We are also producing do it too. Yeah, this is absolute addressing. Yeah, absolute addressing. Okay, I'm going for smoke for and we'll pick this up and hopefully see the end of it. So we can actually add the add instruction, and maybe we will also do we will do call. Call is another thing. So the to-do list would be eventually I have the list somewhere here. So, yeah. So we will have sub. We do have red is simple. That's just single thing. Int 3 is also simple. We can do these rather quickly. And we will do add. That should be the same as sub. And then we need to do calls, and it should be set for some interesting things we can do already with this thing. But the call I will do probably tomorrow. I will have to study how it works, and we will really see. Okay, I'll see you in a bit. Looking for a smoke. Okay, and I'm back. So we need to deal with the absolute addressing, it seems. Let me disassemble this one. What it actually produced. So I'm interested in that. First thing. Yeah, so it's DS. This is absolute addressing format that is used by PC. So this is absolute addressing case code. We will copy this out again. Ignore this one. Delete this one. And put a breakpoint here. Do it. And absolute addressing. Where is that? Where is my absolute addressing? Yeah, this is it. So we should be doing absolute addressing, but we seem to produce incorrect model. This is 34. So let's do the trick again. 34. 34. Copy this one out. Yeah, split it to registers, and this is 0, 0. This is what is expected, but we are producing 0, 4. And 0, 4 is just this one, so we are not even hitting the correct registers in there. Yeah, so the thing for mod_rm is not correctly set. We are not detecting this case. And I guess it's again the same situation, because index is not set, index is 0, and we should be able to pick that up. The base should be 0. Then we would go here, we would set mod_rm to RSP, but we are not doing that for some reason. So let's see why is that. Okay. Memory. We produce. My sound. Right. Yeah, now this is okay. And the D has memory, none, scalar. We have only displacement, so we only want absolute addressing, which can only happen with 32 bits, which is kind of anyway. 64-bit platform. Okay, upcode, correct. On. We set mod_rm to 0 here. That's like default, and it's set to 0. Then we calculate the displacement size, which is only 4, which is correctly right. So we are in here. Signal no index. Now we should detect this case. Yeah. SIP will be written out. mod_rm will be RSP in this case, which was correctly set, and it was the mod rec not correctly set, and they set it to something weird here. Why are they using this one? Yeah, so modreg has this register here set. So let me check what that register. 110 RSI. That's interesting. So they chose to pick RSI as this register case of. So it's not array X. We are using array X for that field. really the field that we thought that was set to zeros, but they seem to be producing this one. I wonder what it is, because I guess it's the assembler specific thing. Because this will detect it correctly, but it should correctly detect even our case. So if we disassemble our case, which is 04 in here. Oh. Completely different instruction, not even increment. Is this some special case? That's interesting. Okay. Six. Oh, is this actually telling us to use? Because yeah, this is actually telling us to use register 6. Because it RSI 6. 0, 1, 2, 3, 4, 5, 6. Oh my fucking god. And I'm not sure whether it's always 6, like in these cases always take 6, or... Because I haven't seen it with pop. Yeah, it's 0. Oh my fucking god, that's so much more complexity in here. So we need to... What we need to do is... uint 8 t unary. In case it's a unary that we are transforming to binary in case we want to generate memory expression, then we need to define these. Well, we don't need to do it here. That's at least that's good. So we only have to do rm back, and so I will put it here, and this is register to use when rm to use on left side on mod rm. We're encoding memory expression. Okay, so in this case it will be rmrec register is 0. So they noted after the opcode as slash number. For example, I will have to write it here because I will completely forget about that. Will be push, which is ff. 6, which is push. The code is ff mod rmrec set to 6 rsi. So that's additional thing that is used to encode the code. And I think I know what this is. And I think I know what this is because modrm what do we have documentation rm here? Okay, so mode here. I'll do full documentation. And this reg thing is not always registered. It's take a look at the manual. On RM and zip bytes. And this reg/opcode field, it's not even reg, it's /opcode. Will specify either a register number or 3 more bits of opcode information. And now we know what it means, finally. So, for example, push is ff opcode with value 6 in this field. And then rm yeah, and there's even something additional to that. I will just straight out copy it because it's quite well written. So there will be cases when the opcode information even spans to RM field. I guess it will be some cases of yeah, there will be some cases with that. We already have some special casing on RM, but this will give us something more in there. Okay. So that's what it is. So that's what that fucking thing is. Yeah, we know now, and this is 6, and now we need to make, and now we need to do it here. So in case it's a mem, then it's not automatically. Let me just do it like this. And this is opcode dot reg. That's what it's supposed to be. That field. This would extend the opcode information. Wait. need to write these everywhere. Push is FF with RM reg set to 6. Pop is 8F with RM reg set to 0. I'm not sure if I get good 8F thing. Right, yeah, I got. Okay, so now this should pass through. Of course there will be compilation errors. No, there are none. Okay, I'm getting better. So let's see, I want to see this. Okay, so we go here and we are trying to encode the unary operation using the binary regmem thing. We need to encode the entire, yeah, and we are now. So the opcode will be RM will be, yeah, FF, and the RM reg will be 6. So this should not pass. Okay. Okay. I'm getting fed up with this. Really, it's just, yeah, I think I know what it is. Let's dissect it again, and 0, 0. So now it's not 3-4, but it's 2C. Because it's still incorrect. Yeah, I know. And this has been +1. The problem is that these all functions take values from this thing, from this enum, and this is offset by 1 because I'm using 0 for no register. This is used for when you don't want any base or index registers. So it means that if I would use register number somewhere as a constant, like in case of RSI, I would use 6. It will automatically be decreased whenever I try to encode it. So we can see that already in this mod_rm, that mod_rm thing, that every time I mention a register, I'm taking a register in, register value, but then I decrease it by 1 because I know that, and also check for whether it's not none. So yeah, that's why it needs to be +1, because in here we are specifying just straight out the value of that. It's not register. Yeah, it maps to register name, but it's really some kind of a arbitrary value of 6. So when we are passing it through that entire contraption, it should be increased by 1, because the contraption at the end will actually decrease it by 1. So it will be 7, and then when we are encoding it, we'll decrease it by 1 to 6, and that's it. So let's try it again. Yeah, it passed. Okay. Okay, let's get rid of that and let's continue. Okay. Out, and let's test the thing. This is not easy. If I knew that I will have to deal with all these kinds of fucking things, I wouldn't probably do it, but I'm stupid enough and ignorant enough to not know these things and just jump on them. And hopefully, because and I have to see it through as well. The thing is that when I don't see it through now, in 1 month I will not fucking remember a single thing, how it works, because I won't be encoding instructions all my life by hand. I will just do this and then I will hope that it's working well. So that's why I need to catch all the possible edge cases now and document as much as possible I can. And also that's the reason why I'm recording all these things, because I want to know and want to be able to just go back to that and find out. I will have to also note these special cases into the document that I will have to do today if I don't really. Okay, so all the tests for push and pop have passed. It teams. So now to make we have disabled some of the tests in the generator, so we will enable it back and run it in full to see whether we have not broken something. I'm also glad that I was able to solve that one. That I didn't optimize the whole code too soon, because otherwise I don't know how I plug it in just by adding like a new field. Yeah, so nearly 8,000 tests. Okay, so final thing for today. Luckily, I'm able to actually partition all these things to some smaller tasks. So we will do adds. That's the last thing. So when I want to add a new instruction, what I do is that I first do this. This is, I know that add will be binary. And when I get back to here, I've copied the sub, so I need to change all these. I need to change all these. So first we will do, not sure I'm encoding the, yeah, but I must be. Okay, so I will add our thing here. I will not test the other ones. I will just do add testing. 64 test, and I'll clean up these specials. Cases. Create the function test special cases. Actually features, to be honest. Not special cases, but these will be features. Because these are things like, hey, I want to do rib-based indexing, or being able to swap the base and index in case it's possible. We want to do RSP-based indexing and things like that. Void x64 test errors, and this will contain, we now just have this one, but eventually this will contain all the error cases. Can happen, probably also generated from a file, features and errors. Yeah, and I will disable. So now we have add. We need to find out what's rmreg version of this thing. So again, manual. Let's find the add function and instruction codes. Add. Okay, so we are looking for rm on the left, this thing. And this is IMM32, so that's probably what we will use already. We can rm IMM32. Already encode that, so this is 81. Okay. Then we need, these are some special cases with array-x. When you want to add something more to array-x, maybe, I'm not sure whether they are shorter or faster or whatever they do, to be honest. Why they are special, I guess it's because of historic reasons, that's why they are there are, but I'm not sure if they will give me some additional value, being shorter or faster or something like that. Then we have that's the first one, and that seems to be, yeah, this is for IMM8, so we can do that as well. And I think I will need, there is some special cases here. I don't know, we will see. we will see, because I need to do these special things like IMM 16, IMM 8, so this is immediate value of 8 bits, immediate value of 16 bits. This is useful because you don't have to encode like 4 bytes, or do 2 of them for 8 bytes, or whatever, however much you need to do that. You can just encode less information, and smaller code equals faster execution. In case the instructions are, of course, interchangeable. So I shouldn't even do these IMM8, IMM32 because this is even use. No, it's not. Yeah, this is. Yeah, these are not even used now, so I won't do them because why? Yeah, but this one is. So RM are not used, but the reg ones are. So need to do these four to do, and yeah, and we don't care about the other. So we need to do the register to RM, the register to. It's not. And where is this used? We will use code. Oh, I see. Okay, so let's document that. Instructions that encode register in not RM and are also able to encode for another expression. Okay. So we need these two for sub. Okay, and we need it for add, but I want to check because this says why I cannot open multiple windows of this, instances of this. I do have 2 of them. Oh, it's just fucking with the windows. Okay. Yeah, I got this one. I think that sub has this register variant, because this has doesn't seem to have like register with IMM. It only has RM versions. The only variant it has is ArrayX yeah, but it doesn't have the. Yeah, here we can see operand 1 is one of these, operand 2 is one of these, and for direct register. So, but I think sub does have that option. So if you go MTU and find sub, yeah, no. So which one did I use for? It's registered to IMM8. It's B0. No, it doesn't have. Let's try to do that. Why didn't it fail something? Because this is from mob, obviously. Not even here. It doesn't have that variant at all. Always RM on the left. And the only case the register is on the left is when subtracting from memory location. And then we have RAX. Yeah. So I plan to actually encode these like a special case on top of like per instruction thing. Before I will see, maybe I will see eventually that hey, these bunch of arithmetic operations do this. So it doesn't seem to have the register on the left anywhere. The only moment it has that is with yeah, it has that is with RAX, and then here we have register 8 bits. So 2A is correct. You can use it here. So this will be the case here as well. And then we have RM. RM IMM8. RM IMM8 is 80. One for sub. Yeah. RM8 to IMM8. Yeah, that's correct. Does it have? Yeah, it does a 4-bit mode. What's this node? 2A, what the fuck is 2A? Yeah. But that's one, and then we have RM IMM32, which is this 83, because you do 64, you do by prefixing it, so the same code we prefix it. I would like to know what this fucking 5 is as well. Hopefully it won't bite me eventually. Oh, I know what the 5 is. I know what the fuck 5 is. I know what the fucking 5 is. Because when you are encoding with memory expression, and that's the target, and not specifying, like that's the expression, and then you are still having one field that is empty because the other side is IMM, and for that thing you will have to, yeah. Oh my fucking this is getting ridiculous. Yeah, so when we did this is the same deal as here, so this is not RMAC, this is actually, we will call it RMOP extension. So this will extend those opcodes in RM. Okay. When we do these, we have to be really careful. And does the other things have? No, these don't have, but the 80 has. We are using 80, yeah, that's the one. And then 83 does have it, and nothing else. And was it 5? 80 and 83, and there is this one. Are we 83 again? Let's be. Oh, this is. Yeah, we don't want this. This is bullshit. Although, if we don't use this one, because this one cannot encode something. Oh, it's just AH. So I think when we are passing in 8 bits of information to sub, probably makes more sense to use these. Seems like so. So we probably can use 83 here as well. How do we say that it's... Okay, so yeah, this is wrong. So this is 83. We will remove this thing. This is 83, but for IMM32 we will use 81/5. 81/5. Yeah, this is what we want. It seems like a more reasonable approach. We will have to, of course, implement this as well. So let me go on. Let's get back to add. And this is add. Okay, so for add we want to encode these as well. So we will have RM register first. RM register is this one is 01. They made this first, okay. This is 01. That's correct. Then we need 8-bit register and RM. It's this thing. Yeah. Maybe there is a better. No, there is not. We still have to use that because we're using this thing. Okay, and this is the same kind of deal in 64-bit. Okay. Okay, so this is 02. Then it's registered to RM thing, so that this is for, and this should be registered to really. We don't care. Register to RM. Register to RM. RM. It's 03. Interesting. This is 03. And is it? Yeah, it goes. It's like 29, 2A, 2B, and 1, 2, 3. It's like in order. And this is incorrect, I believe. If it's already here, then it shouldn't be there. God, I will have to go back. Okay, let's finish this one. So we did this, and now RM to IMM8. RM to IMM8 is 83. Yeah, RM to IMM8, but we need to, and this is 8. Oh, it will be also 83 as it was here, but this time it's 0 in this thing. Gosh, okay. Okay, okay, fair enough. Fair enough. A 0 here. Okay. And then we want what? Register to IMM8. Register to IMM8. Didn't we use... already? What the fuck? What did I fucked up something. Register to IMM8. This one is 80. It's not. One is, yeah, this one is correct. And yeah, register to IMM8. Actually, have any /0 even. So reg IMM8. Oh, will be these. So I assume that register IMM8 for this one will be 80, but with the 5 operator extension. Starting to getting lost in it. Going for smoke. Okay, so there is one more gotcha here. Because I think we also need to do size of the register. This one, for example, adds this O2 thing, yeah. This will also cap our. So we can only use this one when the register size is 8. Also the memory is 8. So this has to be explicit. You can use whatever size. You encode it somewhere. RM, I guess. And we need to be explicit, really. This is also for any size, but these are like special ones. Generally, you can use just O3 for addition. Yeah, O3 when you encode the register to opcode. And then with prefixes, you can, I guess that you can use a 16-bit prefix until form specify. We don't do these yet. We only do 30. But eventually I will do the 6. But generally it can encode both. That's all right. Yeah. Okay, so now these two things, I need to go really closely about them because IMM8. So we are using 83 here, 83. Yeah, and it takes whatever on end. It can take 16, 32 or 64 on the left side, but only IMM8 on the right side. It's correct. Whatever on the left for both. No, this is for IMM. Yeah, whatever on the left, but IMM on the right. And this one takes maximum of IMM 32. Then sign extend. So there is a interesting thing with immediate values on 4-bit. Think that if you really are calculating with 64-bit immediate values, then you have to go through a register. You have to first store the value in the register, then you have to do the add operation with register memory. Yeah. Okay, so this one is correct because yeah, it takes only IMM8 on right. This one, 81, is this one. It can take whatever on left side. So yeah, we have it named correctly. It's RM without a suffix, size suffix, and IMM 32 on right. So that's correct. So okay, we need to do the same for this one. And now register IMM8, which we used 80. So 80 is here. So this can take only register 8 size register on left and 8 size IMM on right. So I guess this would be reg 8 IMM8. So it's reg 8 IMM8. Okay, and we need to find out what this thing is using. Because we have it defined for Nova. But we need to revise Nova as well. Revisit it. Maybe not. Let's check it now, because now we know that all these things are correct for add. We will do Nova now, and then we do go back to sub and fix the sub as well. So let's go to Mov now. Mov. Okay, so for Mov, we use 29 for like generic thing. It takes whatever. No, 89. Sorry. 89. Yes, so it takes whatever on left and whatever on right. That's correct. Then we have, I think I should write like generic ones first. Should be this one and that one, and then we will use the special ones, because this will help us optimize the thing. If we set this up correctly, it will help the assembler to produce smaller code. It will help with speed. So now, next we will do ones that have, yeah, this should be like the last thing here. I will reorder this one as well. So first we start with the general ones, and we end with yeah, this should go here. Go here. Yeah. Okay. Yeah, so we have generic ones here, then we have limited on one side here and limited on both sides here. And we should also reorganize this one. So this will be the last one. And this will also have the up field. Then we have, and always register is the first one. Although the fact that it takes register on the left side, special case as well, it's like optimization. Don't have to put RM. So I will consider this one as somewhat here, because this is more generic than this one. Okay. So this one should go here, and this one also needs the up thing. We have reg IMM 32. Not sure if that one is even set up somewhere. Yeah, here. We have it here. And that's a B8. B8. Is the B8, yeah. So this takes whatever on left and IMM, even IMM 64 on right. Okay, but this one doesn't sign extend, as opposed to the version. So we can technically just call it this way. Register has to be 64, right? Yeah, I think we have to go even further with this. Even further, because we now need to it cannot take IMM64 with any register. Yeah. So this one cannot take for 10. 1064. It can take 64 with it on the left. Because then the IMM will work. But I think this is not correct. It should be good. Really. Yeah, I think it should. So goes with all these optimized version, and doesn't say any extension. Yeah, the registers encoded in the instruction. Okay, so it doesn't need any opting, and this one neither. So these are okay. So this is IMM64 and IMM32. So this is register 64, register 32 to IMM32 would be the same thing actually. Yeah, because it's B8. Yeah, we need to be explicit about these. Even though they have the same opcodes, they have to be specified closely. So then we have register IMM8. That's okay. B8, B0, 0, B0, B0. Yeah, it's these two. But there is a note in here. Yes, again. This one, yeah. Same kind of a deal. It seems to be the same kind of a deal for 8A. Yeah, it's done that. Okay. Fine. We will be okay. It's getting a bit more complex with choosing the opcodes, but. Oh yeah, I'm on the all time. Okay. Thanks, Alexi. Yeah, whatever. It's getting really hairy up in here. It's like it's terrible. I hate it so much. But if we get it right, I think we should be okay. I think we should be okay. We just need to be really careful about those sizes, because if we try to generate code, that will start to cut off the bits. Especially with arithmetic operations. Like with math, it doesn't matter. It doesn't really matter because okay. But with add and sub, like arithmetic operations, start to get very. And I'm thinking about whether even support these things. Like, can I have? Like, I want to kind of minimize it at this point, the number of possibilities of the whole thing. Because it's getting really complex. So I think part of it is informed by these arithmetic operations. So I think we will need like RM reg RM are okay for add and sub. This is alright. We can do whatever we want with that. We then need RM and IMM parts, and that's it. I wouldn't go for anything else. Like these, fuck them. Because these are optimizations that we can choose better things. But for now, just to minimize the space, we go for them later. The problem is that these things might be generated by the assembler that we are using for testing bytes. So I'm not sure. I think we should keep them in, but try to work out the code for only the first 4 ones. Like these are the base. This is the base that we need to define for everything. So here we're missing dot. This is not even important right now. We have reg, okay, B0 dot. B0 is 88, so this is special case. Okay, this is 88 for IMM, so it goes here. Yeah. As it always just unaligned. Okay, and we need RM IMM8. This is the first one. RM IMM. This is the one. RM8 IMM8. Yeah, but there's like not there's not even like an instruction for generic left hand side, but that's okay. It's okay for MOV, but it's not okay for additional subtraction. So we need to do, this will be probably even incorrect. Is actually RM8 IMM8. Yeah, RM8 IMM8. RM8 IMM8. So RM8 IMM8 is RM8 IMM8 is C6 or more, and we need to encode this up thing 0, which is as well. This is also up. Thinking whether there would be some kind of possibility of abstract this, like write some arrays or something like that eventually, and not to use. Why is it always unaligned? Why? Up, and this is 0. So C6 over 0. Okay, and then we need RM32. IMM32, which will be also, oh no, that will be C7 with the 0. 7 with the 0. So that's one. That keyboard switching. Okay, so this is okay. These need to be just down like this. So we have two general ones, but then for everything else, these are more generic ones because these are basically encodings of the IMM. And some of these even have, yeah, there is register 64 to IMM 64, and is there a memory as well for that? Like RM 64. Yeah, this one. No, this is 32. Okay, so we only have register to or something more. Don't have RM64 like this on left. With IMM64 on right. IMM64 is only used once in this case. I don't see it anywhere else. Yeah, that's the idea. Okay. Okay. These are the same things. They don't have, but also these have. This is like register, yeah, it doesn't have anything else. it seems like the operator operand register in bytecode in opcode. Okay. Then BO is here. This is also registered in bytecode. I mean opcode. Then we have 8A, and that's also registered in opcode. Yeah. So it seems like general idea is that whenever the register is on the left, then it's part of the opcode. Whenever we will be encoding these, the register on the left, except for when. That's interesting. Wait, doesn't make sense. No, this means that register is in mod RM R. Yeah. Yeah, register. So again, 8A register in mod RM, right? Okay, and let me check again these. Yeah, this is RB. This things means that it's in instruction. In the output. Okay, so whenever we have RM, okay. This kind of makes sense, it's kind of obvious. Yeah. Okay, now back to these ones. So these ones are correct. C7. 7. Yeah, and that uses RM. But it also uses these extra because we are not using any registers, so we can use the register number in mod RM for these, so it makes sense. And this one doesn't make sense. Yeah, this do make sense. We have register 8, RM8. What else?